2.5, implicit differentiation. So to understand the value of implicit differentiation, let's take a look at an example here. If I have a function defined in this way, xy equals 1, that function is defined implicitly. And for a simple function like this, we actually have a choice. We could solve for y and get that function explicitly. So up till now, this is the only kind of function that we know how to differentiate. We have to get the y isolated on the left before we can take the derivative. But what we're going to find today is that we don't necessarily need to do that. So when would that be useful? In this case, we could have a choice. We could either solve for y and take the derivative explicitly, as we've been doing, or we could use this form and find it implicitly. But there's other times when we don't have such a choice. Look at a relation like this. In this case, we have multiple terms with y cubed, y, y. In this case, it would be very difficult, maybe impossible in this case, to solve for y and get this relation in an explicit form. And so it's really for examples or problems like this that this implicit differentiation comes up to be so useful for us. We're not going to do one like this right away. This is a pretty difficult one. Lots of terms. So we're going to start with a little bit easier ones to kind of get an idea of how we differentiate these implicit expressions with respect to x. We have to be really careful to use all the rules that we've come across so far. We're going to come across power rules. We're going to use the chain rule. We're going to use product and quotient rules. So we have to be able to really apply those in a careful way in order to do implicit differentiation properly. So this first one, kind of an easy one. Differentiate 3x squared with respect to x. Alright, so these are the types we've been doing all along. So we have a power rule here, so this is just going to be 6x. No problem there. Right. The next step gets us going on this road to complications. Right. We have the derivative with respect to x of 2y cubed. Right. Y itself is a function of x. So really what we have here is we have a composite function. So whenever we take the derivative of y with respect to x, we need to use the chain rule. Right. And here's how we would apply it in this case. The derivative with respect to x of 2y cubed, we're going to apply the power rule first. So this exponent comes and multiplies by the 2. So we have 6y squared. Now the derivative of the inner part of y is dy dx. That's the chain rule part of that problem. Take a look at number 3. Taking the derivative with respect to x of this sum, x plus 3y. So the derivative of x with respect to x is just 1. The derivative of 3y with respect to x. Notice that this y is not raised to any exponent, so all this is 3 dy dx. The last one on this page is the derivative with respect to x of this product, x times y squared. So to take the derivative of this product, we need to use the product rule. And when in the process of using the product rule, we take the derivative of y squared, we're going to need to be careful to use the chain rule. So we have to combine these two. So let's do it this way. I'm going to apply the product rule here first. All right. So I have basically my f and my g. So the derivative of x is 1 times y squared plus the derivative of y squared times x. And you'll notice that I didn't actually take the derivative of y squared yet because I want to do that in the subsequent step so we can see what's happening there. So I'm still left with y squared here plus, now when I take the derivative of y squared, I have 2y now to the first power times dy dx, using the chain rule there for that composite function, times x. And I might clean that up a little bit by writing y squared plus 2xy dy dx.